Now let's talk about resistors. And basically resistors is a family name. It's a family name that has several applications of resistors, brackets of resistors, different technologies of resistors, and I want to go with you through some of the technologies, kind of a top-level description of each of the four technologies of the standard low-power resistors. There are four different technologies. The one on the top has a carbon fill-up between two end plates, and it's all mounted inside an insulating material. This insulating material, we're talking about the picture on the top, this insulating material is one that can let the heat be dissipated easily. In other words, every increased temperature that is being generated within the carbon, inside the carbon, is transformed to the other side, is transferred outside through the insulation material exposed to the air and dissipate. The second one from the top is carbon cylinder. The carbon itself is a resistive material, and the carbon cylinder is being held with two caps, two ends, insulating material. We have a carbon film, the third one from the top, carbon film, which is basically the resistive material again, and again is connected to the two end caps with the two conductors on the two sides, the insulating material, helping the heat that being generated inside to be dissipated to the open air. And the last one is wire wound. Wire wound is very precise and high power resistors. We will talk about it later in the course. And the wire itself is the resistive material. It has no carbon inside. It's just the wire itself is, and the wire itself is made of material that has high rho. Okay, high rho means that the unit of resistance per length is very high. Very easily we can control the length of the wire. We can control the diameter of the wire. Therefore, we can control very precisely the resistive area, the resistive material. Therefore, the resistor itself. So wire wound resistors are precise resistors, and also if we increase the diameter of the wire being wounded on the base material of the resistor, we can increase the resistivity. Power dissipation and sizes. Now in resistors, we actually look at low power, mid power, and high power resistors. And it's all to do with the ability to dissipate heat. In low resistance resistors, the current actually is very high, because resistor by its nature is to limit the current flows through. The lower the resistance, the higher the current. The higher the current, the higher the power. The higher the power, the higher the dissipation, the heat generation, and the needs to dissipate. Therefore, we need more area, surface area, around the resistor, so more heat can be contacted with the air and dissipated more effectively. And we can see on the picture, on the left-hand side of the picture, we can see a quarter of a watt. The measurements are on the right-hand side in millimeters. And then it goes to half watt. These parameters, these values, 0.5 watts or 1 watt, or even in the metallic aluminum resistor on the lower left corner, is 25 watts. It's the maximum rated power to be dissipated before the resistor gets burned down. It's the maximum allowed power to be dissipated, which basically means the maximum value of I squared times R. So we can see the different charts, different set of resistors here. The right-hand side is the measurements, the left-hand side are the types
together with the color code. We will talk about the color code, but the more emphasis I would like to say kind of more about the power transistor made in metal. This is an aluminum type of cover, and as we well know, aluminum lets the heat transform and transmits very, very easily. This is the reason we use it as a heat sink. It actually takes all the heat which is being generated inside the resistor and sink it out to the open air. The reason that we have these fines on the aluminum is to increase the surface area and the contact area with the air. It's much bigger than if we do it with just a smooth aluminum case. The reason that we have these wings is to increase the contact area to the air. If we increase the contact area to the air, we actually increase the total area where the heat is generated, meaning that the heat density per given square millimeters or square centimeters will be lower, so the lifespan of the resistor will be longer. We want to reduce the heat density around the case, all over the case of the resistor. And we have different applications for resistors. We have power, precision on the second left, we'll talk about it in a minute. We have a surface mount resistors in different technology, we'll talk about that. We have the high temperature, all the way up to 300 degrees centigrade. We have the high voltage, 2 kilovolts. And we have the network arrays, which are basically a component that has a network of resistors within that array, legs coming out, and between the legs, based on technical specification, we actually can connect different resistors in an array. It can be 6 resistors within an array, 12 resistors within an array, all within one package. Obviously, very, very low power, almost no heat generated that should be dissipated. So the arrays, low power resistors. So let's look at the power resistors on the left. We can see the level of accuracy, the tolerance. The tolerance over there will be 0.1%. This is very precise. Now, please keep in mind, powered resistors and high precision resistors. Normally, actually, they don't go together because as the temperature rises, it changes the resistance material, the resistivity of the material itself. But yet, the tolerance, it can go down to 0.1%. In the precision, the second one from the left, the precision also goes to 0.005%. Very precise resistors. In terms of power, no choice. The power is very low, 0.125 watts, up to 1 watt. So it's very low power, but we gain precision. Very important. The one on the center, surface mount resistors. Surface mount resistors have basically no legs that go in through holes in printed circuit boards. We solder them on the component side of the printed circuit board. And this is what we call surface mount. It's what we call SMT, surface mounted technology. These resistors, very low power, 0.1 watt all the way up to 50 watts. 50 watts is middle, but the precision is there, 0.1%. And remember, the two end caps on the body, they are the leads where we solder them to the printed circuit boards. Then again, we have the high precision temperatures. Sometimes we go out to 10 watts, the high precision, the high temperature, all the way up to 300 C. And the reason that we stop in 10 watts is because it can withstand 300 C. So there's a trade-off between the value of temperature, the maximum value of temperature that the resistor can hold, can work by, can operate, and the total output power that the resistor is. Again, it's very precise, 0.005%. The high voltage, between 1 watt and 15 watts, somewhat less precise, and the tolerance is shifted to 1 to 10%, but it's for high voltage applications. And like we said, network and arrays set of resistors within one package, very, very low power resistors, 0.3 to 1.35, very, very low, because basically if we have 6, so it will be 6 times 1.35 watts, will be something about 8-9 watts. In a very, very small case, we need these watts to be dissipated, so this is why it's on the lower end of the output power. And it's precise, 0.1% to 5%. 5% is on the non-precise end, but 0.01% is definitely a very precise one. And the high power, let's see how they built. We remember the aluminum case. We remember the fields, the wings, in order to increase the contact area to the air, in order to decrease the heat density per given area. And this is how actually they build. We have this case, of course. We have the core. We have a mineral insulation between the core and the case. And terminal legs come on both sides, and we have a mounting legs. And basically we have a fiberglass rod at the center of the core, on which the resistive material is either wounded or spread around. So we have fiberglass core, we have the resistive material, we have insulating material, and all goes inside into this aluminum case. Ceramic wire wound. These ceramic large, I'm doing something with my fingers because it can be 30, 40, 50 centimeters long, and they are very heavy. There's basically a ceramic pipe that is wire wounded. So they're very accurately done, and very low tolerances, 0.005%. And the ceramic acts as a core. The wires being wounded on, we can determine again very precisely the resistance of the wire, because we can control the diameter and the length. And in between, we can see the one on the left. There are two end connectors, and there's one in the center. This one in the center is basically divides the resistor into two sections. The one on the left with the center, and the one from the center to the one on the right. So it's resistor number 1 and resistor number 2. We can actually ignore that particular connector and have resistor number 3, which is the altogether resistance from end to end of this ceramic resistor. But they are high power and very precise. And if we continue one additional minute on these ceramic high power, some of them, for higher even power, have holes inside to let the air goes through, cool the resistor down, take all this heat and force it out. So eliminating heat pockets inside. And this is an excellent idea specifically for very high power electrical applications. And we discussed, we mentioned before the color code of the resistors. Let's look at this. There are certain codes by which everyone who deals with resistors, designers, users, technical maintenance people, that when they see a resistor, they can read and understand its value in terms of ohm. How many ohms does this resistor have? And we have a 4-band color system, we have 5-band color system, and we have 6-band color system. And on the right-hand side of each resistor, we have the level of accuracy and the temperature coefficient of this particular resistors. So the entire story, the entire technical specification almost is coded on the outside insulating material of the resistor. So let's look at what is every single line, every single strip. The one on the left is the first digit. The one on the next to it is a second digit, third digit, and then comes what we call a multiplier. Let's look at the resistor on the top. It says that the resistor is 256 kilo ohm. And let's see how it does. Red is number 2, so it's 2, the color code of the first digit. Green is 5. You see the second row on the chart, the color chart. And next to it is 3. That means that it's 2, 5, and 3 zeros. That means 25K. 25 kilo ohms is red, green, and orange. Now, further away from it, in a 4-band color code, is the tolerance. And if it's gold, it will be 5% plus minus. If it's silver, it will be 10 plus minus 10%. And if it will be different colors, we can see the tolerances. So even if we say 25,000 ohms, 25 kilo ohms, because it's red, green, and orange, it actually say it's 25 kilo ohms plus minus, depending on the color of the tolerance. If it will be silver, it will be plus minus 10%. So the 25 can be anywhere between 22.5 to 27.5. The nominal value is 25. Now let's look at the tolerance. And now we have a temperature coefficient. All the units of ohms, all the resistance, are basically measured based on ambient temperatures. Now, the resistance changes as the temperature changes, and the temperature coefficient is marked on the 6-band color code only on the very last color ring. And we can see 100 ppm, ppm stands for parts per million, 100 ppm, 50 ppm, 15, 25 ppm, very, very accurately for each additional 1 degree centigrade. Just as we had the idea, the concept of arrays of resistors in one package, we have what we call a 16-pin DIP. And DIP stands for dual inline package. This is in a configuration of an integrated circuit, same measurement, same material externally, same type of legs, distances, everything is the same. It's just that inside it, we have a matrix, an array of resistors. Again, very low power, very high precision, low tolerance, but it's in one package, and we can use them for pull-up resistors, pull-down resistors. We'll talk about it later when we'll deal with circuits. I just wanted you to know, to be aware of the idea of an array inside a DIP, dual inline package, just similar to integrated circuits. And here is the family of the surface mount. Let's look at the picture. Even to measure it in millimeters, very easily you can see the variety of the SMT resistors, surface mount technology resistors. And in terms of what's written on the resistor itself, the two sets of black resistors, that some of which are surrounded by red elliptical thing, we see that they're, like for example, the one on the right hand side, 4.7 mega ohm, in other words, 4.7 millions of ohms, 4.7 mega ohm. It's written in one way, and there are two different codes in terms of how to read. It's written in both ways, and they're both okay, just different standards. And let's actually evaluate the two different standards, the upper line of resistors and the lower line of resistors. And the ones that are circled in green elliptical shape are jumpers. They are basically components with no resistance. They are short. They are 0 ohm resistance. So there is a short between both of the end caps. In many cases, in electronic circuitry, we need to connect a jumper between 2 points, which is for one particular application, and for another application, we'll just take off this jumper and solder a resistor that has some resistance. So, and this changes the personality, the features of the device itself. So, and we will do that when we'll talk about the circuits. So there is a need, so from time to time in circuitries, to solder a short, to solder a component just to fill up the space that has no resistance. It's just like a jumper, a connection between one point to another point using a device. Sometimes in the future, this device will be replaced by a true resistor with the same shape physically, but have some resistance. Here is some example of the SMT resistors, surface mounting technology, SMT, on a board. And look, the resistors have no legs. There are no holes in the printed circuit board. They are actually soldered. Each case, each physical case has 2 end caps, 2 metal caps, and they are actually holding the carbon or whatever it will be there, either the wire wand. And these are the leads of the resistor, and these are the 2 things that are soldered to the board. And I've just decided to share with you a table of measurements, just so you'll see how small things are within the surface mount technology. So we have the sizes here starting from in inches and in millimeters, starting from 0.5 millimeters. Very, very small, meaning very low power, meaning high precision. So here are the measurements, here are some charts, here are the different types of the family of the surface mount.